Sometimes the most amazing ideas come from smashing two completely different fields together. Like, you take a concept from deep in physics, and all of a sudden it gives you a brand new way to look at something like economics. And that's exactly what we're diving into today. A really wild idea that uses the built-in mistakes of a quantum computer to understand financial risk. It's a question that keeps people up at night, whether you're a Wall Street trader or a systems engineer. Why do two things that have always moved together in perfect sync suddenly just don't? Why does the supply chain that's been running like clockwork suddenly snap? This breakdown of things we count on is a huge, huge problem, and it's incredibly tough to predict. All right, so let's start with the absolute core of the problem this research is trying to tackle. It's that moment when all our models of the world just fail, when things stop behaving the way they're supposed to. Think about it. Economists and investors, they build these super complex models based on years of data. They'll say something like, okay, when oil prices go up, airline stocks should go down. Makes perfect sense, right? But then some global crisis hits and suddenly they both tank. The correlation is broken. And that's a massive challenge for anyone trying to manage risk, because it's always the unexpected that really hurts. This whole phenomenon actually has a name: economic decoupling. It's the official term for that moment of total surprise when two partners in a financial dance just decide to go their own separate ways. And trying to figure out the probability of this happening, well, that's pretty much the holy grail of risk management. So how in the world do you get a handle on that kind of uncertainty? Well, a recent research paper has a pretty radical idea. It says, hey, let's forget about economic history for a second, and instead, let's look inside one of the most advanced and, frankly, flawed pieces of tech we've ever built. You heard that right. The core idea from researcher Mohammed Sukri bin Romley is to take the bugs of a quantum computer, all the noise and errors that physicists are working around the clock to get rid of, and actually turn them into a feature. What if the way a quantum system messes up is a direct analogy for the way an economic system breaks down? Now, to get this, we need to talk about something called a Bell state. It's one of the most fundamental ideas in quantum mechanics. So imagine you have two quantum coins, and they are so deeply connected, or entangled, that if you flip them, they will always land on the same side. Always. Heads, heads, or tails, tails. They are the perfect pair, a system where the correlation is absolute. Well, in theory, anyway. Okay, let's really dig into this, because this slide right here is the heart of the entire idea. On the left, we've got the quantum world. In a perfect noise-free quantum computer, those two entangled qubits would always match. But here's the thing, these machines are noisy. They're still in their early days. So that noise causes errors, and sometimes you get a mismatch. The perfect link is broken. Now, look at the right side. It's our economic analogy. Two indicators should move together, but real-world uncertainty causes them to decouple and fly apart. You see it? The quantum mistake becomes a direct mirror of the economic breakdown. So, and this is the crucial point, the rate at which the quantum computer makes a mistake, the probability of getting that mismatched result, isn't just a clever metaphor anymore. It becomes a physical, measurable number that acts as a direct proxy for the probability of that unexpected economic decoupling. You're not using old data. You're using the actual physics of the machine to generate a risk number. It's a completely different way of thinking. All right, so this is a super cool idea, right? But is it just an idea? No. The researcher didn't just write about this. They actually went and ran the experiment on a real quantum computer. So they used IBM's IBM Quantum processor. The goal was simple, just try to create that perfect pair Bell state. But here's the really clever move. On a quantum chip, not all the parts are created equal. Some qubits are just higher quality, less noisy than others. So the researcher tested two different pairs on the same chip, a high-quality pair and a lower-quality one, to see if the error rates would actually be different. And the process was super rigorous. For each of those pairs, they'd run the program to entangle them. Then they measured the result over 4,000 times to see just how often it messed up. And just to be sure the numbers were solid, they repeated that whole process 5 times for each pair. Okay, so they ran the tests. What did they find? This is where it gets really, really interesting. Just how noisy were these different parts of the same machine? For that first high-quality pair of qubits, the average error rate, our decoupling probability, was incredibly low, just 1.6%. Think of this like a super stable economic partnership. Out of 100 times, more than 98 of them go exactly as planned. It's predictable, it's reliable, it's low risk. But what about the second, lower quality pair on the exact same chip? The error rate shot up to a whopping 9.2%. All of a sudden, that stable partnership is incredibly fragile. You've got almost a 1 in 10 chance of a total breakdown, making this part of the system nearly 6 times more unpredictable than the first one. And this chart just lays it out crystal clear. On the left, you've got the stable system with that tiny little error rate. On the right, the much more fragile system, way more prone to breaking down. And remember, this isn't a theory. This is a physical measurement of how inherently stable or unstable these two systems are. So you gotta ask, why the huge difference? Well, the answer was right there in the machine's own diagnostic data. The qubit pair with that high 9.2% error rate also had a much higher average readout error. We're talking about 9% versus less than 1% for the good pair. So this totally confirms it. The physical flaws of the hardware were directly responsible for that higher chance of decoupling. But wait, it gets even cooler. What if you could digitally clean up those errors after the fact? The researcher applied a software technique called error mitigation. Think of it like a statistical cleanup crew for your data. And the results were just stunning. For that noisy pair of qubits, the error rate dropped from over 9% down to basically 0. And as the paper puts it, when you correct for these measurement errors, you get to see what the true, ideal system underneath is really doing. The economic analogy here is just so powerful. It's like an economist realizing their way of collecting data is flawed. Once they fix that, they get a much, much clearer picture of what's actually happening, separating the real signal from all the noise. Okay, so let's pull back for a second. What does all of this actually mean? What's the big takeaway from this really fascinating experiment? Now, it is crucial to understand this. This is not a crystal ball for predicting if the market will go up or down tomorrow. That's not the point. Its value is something much more fundamental. It gives us a new way to measure a system's inherent fragility, its built-in potential to break, based on its physical properties, not just on how it behaved in the past. So, if you're going to remember just a few things from this, make it these. First, a quantum computer's noise isn't just junk. It can be a real, measurable stand-in for real-world uncertainty. Second, not all systems are created equal. Some parts are just physically more fragile than others. And finally, this gives us a brand new way to think about risk, one that's grounded in physics instead of just spreadsheets of historical data. Now, this whole quantum approach isn't meant to replace the traditional economic models we've used for decades. It's meant to be a complementary view. Think of it like getting a new kind of sensor. Your old sensors still work great, but this new one, it measures something you could never see before. The system's deep, intrinsic vulnerability to just falling apart. And that leaves us with one final pretty mind-bending thought. For decades, the goal's been to build perfect, flawless computers. But maybe, just maybe, we've been looking at it all wrong. Perhaps the most valuable thing these strange new machines can teach us comes not from their perfection, but from their flaws, giving us a powerful new mirror to understand the beautiful, messy, and flawed world all around us.